In this supplementary lesson, we're going to study something known as RSA encryption, or at least a slightly modified version of it. You do, however, have to know what modular inverses are. It will also be necessary to know how to execute the successive squaring algorithm and how to compute modular inverses in general. We're going to take it as a given that any message you would want to encrypt and send someone is actually just a number. There are lots of ways to convert text and symbols into numbers, but the quickest thing we're going to do is we're going to use 0, 00 through 26 to represent letters, and then 27 will represent a space. So if we want to encode the word gremlin, we're going to convert it into the following number. G is 07, R is 18, E is 05, M is 13, L is 12, I is 09, and N is 14. Altogether, we just have this number that now represents the word gremlin. Notice it starts with a leading 0, but that's not really a problem. We could also interpret the number 03, 08, 05, 05, 19, 05 as 03, 08, 05, 05, 19, 05, and then back convert into letters cheese, C-H-E-E-S-E. So we're just going to work under the assumption that our only real task is we have a number that represents a message and we want to securely transmit it to a desired person. We're really not going to focus on converting text into numbers. We're just going to assume that's done. And the message that we need to send is some large number. So now let's suppose we have a number and we want to transmit it to our friend. 0718 05 13 12 09 14. It's imperative that our friend get this message. But we're in a crowded room and everyone else is our enemy, so we can't have them understanding it. How am I going to deliver this message to our friend without anyone else knowing what we're saying? So some encryption schemes rely on the fact that the method of encryption is not known by your enemies. As a really simple example, we could say shift all the numbers by adding 1 modulo 10. So while our original message was 0718, we replace that with 1829. 0513 becomes 1624. 1209 becomes 2310. Notice I replaced 9 by adding 1 to it, it became 0. And then 14 gets replaced by 25. So I say this number out loud instead. Now if someone listens to that, they won't be able to understand it. 18 happens to correspond to the letter R under our previous conversion scheme, but 29 is not a letter at all. So they're going to think I'm just saying nonsense. Our original message, by the way, does have an interpretation as letters, 07, 18, 05, and so forth. This encrypted version doesn't. But now we have a different problem. How can I tell my friend that's what I did? How do I let them know what I did was add 1 to every number? If I just said out loud, oh, hey, buddy, I'm adding 1 to every number, then everyone else is going to hear that and they're going to know how to recover the message as well. So the question would then become, how do I tell my friend in secret what method of encryption to use? Well, if I had a way to secretly tell them what encryption method I'm using, I could have just used that method to send them the message anyway. So if we can communicate secrets, then we don't really need to encrypt things. We just use that method. In contrast, a public key system is one in which everyone knows what the encryption method is. The method of encryption is not secret. Everyone knows how it works. But somehow, it's still the fact that only your intended recipient can understand what the message is supposed to be. In 1976, 3 people, Ron Rivest, Eddie Shamir, and Leonard Edelman, proposed a system which is now abbreviated as RSA after their names. Here, what we're presenting is slightly modified from theirs, but the fundamentals are the same. In fact, a few years earlier, an equivalent technique to this was developed by GCHQ, a British intelligence agency. It's widely believed it wasn't actually implemented to any great degree just due to computational issues. And because it was developed by an intelligence agency, it was kept secret for many years until 1997. So this method was probably developed a little bit earlier by someone in this British intelligence agency, but it wasn't really widely implemented at the time. And the version that spread is RSA. Let's suppose I want to send a message to Alice. Okay, what she's going to do is make her public and private keys. So she sits down and does the following. She finds two distinct odd prime numbers, p and q. She doesn't tell anybody what they are, okay? So there are methods for finding large prime numbers. We're not getting into that, but computers can find big prime numbers reasonably fast. Okay, and by big, I mean a few thousand digits long. Not record-setting big, but pretty big. Okay, so they should be pretty large prime numbers, and she doesn't tell anybody what they are. But because she knows what p and q are, she can compute the product p times q. We're going to call this capital B. Next, since Alice knows the prime numbers, she can compute phi of b. PQ is just b, so she computes phi of PQ. These are two distinct odd primes, so it's phi of p times phi of q, and since they were primes, that's just p minus 1 times q minus 1. Okay, this number, phi of PQ, she also keeps secret. Alice now picks another number k, which is relatively prime to phi of PQ. Since she knows the value phi of PQ, she can use the Euclidean algorithm to verify that k and phi of PQ are relatively prime. Alternately, you can just pick another prime number that's reasonably big. Okay, and again, because she knows phi of PQ, she can compute the inverse of k modulo this base. Okay, because she ensured k and phi of PQ are relatively prime, this inverse exists, and she can compute it because she knows phi of PQ. Whatever k inverse is, we're going to call this number j. This number j is also kept secret, and it's what's called Alice's private key. The inverse of k modulo phi of PQ. What she does now, however, is she publicly announces, I'm working modulo capital B, which was this product, and my exponent is k. What's important to point out, however, is that even though Alice says, I'm working modulo B, she did not tell anyone what the two prime numbers p and q are. So for example, if the two prime numbers were 5 and 11, she would just say, I'm working modulo 55. She knows it was 5 times 11, but everyone else might not know that. And again, factoring large numbers is very difficult. Multiplying large numbers is easy. So her two prime numbers, she easily multiplies and gets another enormous number. But when she announces this out loud, it's very difficult for anyone else to know which prime numbers were used to create it. So this pair, the exponent comma the base, is called her public key. So that pair is known by everyone. Alice keeps secret j, which was k inverse modulo phi of PQ, the inverse of the exponent modulo the Euler-Totient function of the base. Okay, and in order to compute this, you would need to know phi of PQ. In order to compute phi of b, you need to know the factorization of b. And again, most people are not going to be able to recover the two large primes just because they know the product capital B. So the exponent k and the base capital B are publicly known by everybody. However, the inverse of the exponent modulo the base is Alice's private key, and she keeps that secret. So in fact, if fast factoring algorithms were developed, then people could in fact recover the original primes from knowing that base capital B. If that ever happens, RSA encryption will no longer be especially secure. If someone else is able to compute the factorization of B, then they'll know what two primes went into it, so they'll be able to compute phi of PQ, and then they'll be able to compute k inverse modulo that base. So the security of this technique entirely rests on the fact that capital B is difficult to factor as the product of two primes. So faster factoring algorithms are the subject of great research. It would be very interesting to find them, even if socially unstabilizing. Also, there are different types of computers that may be able to execute very fast factoring algorithms, specifically quantum computers. So far, however, it doesn't appear to have been done on a practical scale. Big asterisk there. That's basically how people are expecting this method to fall apart. A quantum computer being able to quickly factor very large numbers would instantly mean that this method is not especially secure anymore. So how do we send Alice a message? So you know Alice's public key, so does everyone else, okay? An exponent k and a base capital B. You want to send her a message, the number capital N. Remember that only Alice knows her private key, the inverse of the exponent k modulo phi of the base. So what we do is we can take our message n and we raise it to this exponent and we reduce it modulo b. So we just have to use her exponent k and the base b. We compute what is n to the k modulo b. So we do something like a successive squaring algorithm to quickly compute this. Whatever the result is, let's call it capital M. Okay, it's a very, very different number from n. It's n to the k reduced modulo b. So what we do is we very publicly and confidently just say, here is my number m. Alice takes the number m and computes m to the j modulo b. Now remember, j was her private key. Presumably, no one else knows the number j, only Alice knows it. M to the j is equivalent to n modulo b. Why is that? So j was k inverse modulo phi of pq. Only Alice knew what phi of pq was, so only Alice could compute the correct inverse because only she knows this base phi of pq. So what we know is that j times k is equivalent to 1 modulo phi of pq because their inverse is modulo that base. In other words, j times k is a multiple of phi of pq plus 1. So then what we do is we check the following. We had our message m and Alice has raised it to the j. How did we compute m? It was equivalent to n to the k. But n to the k to the j is just going to be n to the j times k. J times k is a multiple of phi of pq plus 1. So I factor out this n to the first, and then what I have left is n to the x times phi of pq, which I write as n to the phi of pq to the x. So using her secret exponent j, and my very publicly announced value of m, which is just n to the k, Alice computes the following and gets this result. But remember, if n and p times q are relatively prime, then n to the phi of pq will be equivalent to 1 modulo b, and this will just be a 1. So m to the j will be equivalent to n modulo b. So using her secret exponent j, Alice can recover the original message n. And that's it. So let's talk about how this algorithm works. Okay, all computation is being done modulo b, so there's a limit on the size of the number that can be effectively transmitted. If I'm working mod 10, the only numbers I can send are 0 through 9. Okay, so the base that we're working needs to be quite large so that we can accommodate very large numbers. In other words, we can accommodate lots of different possible messages. So if b is very large compared to the size of the message being transmitted, that's fine, that's taken care of. A very, very long message is then not sent all at once. Okay, so suppose you are able to transmit 50 characters at a time. If you have a long piece of text to send, you just break it into pieces of 50 characters at a time and send each one. We also at some point had to assume that our message n is relatively prime to the base. Okay, and remember, when we make our message n, while we do know the base, we very much do not know its prime factorization. That is not something we can reasonably compute. So how do I guarantee that n is relatively prime to the base? Well, in practice, it's extraordinarily unlikely that it won't be. Okay? There are ways to get around this possible problem. Now, since b is the product of two primes, even if I don't know what the primes are, I do know this technique works in this manner. So b is the product of two primes, and n is not larger than b. In other words, it's from the standard complete residue system modulo b. Okay? So it is in the complete residue system mod b. We just need to guarantee it's in a reduced residue system mod b. Now, phi of the base is phi of pq, which is p minus 1 q minus 1. That's the size of the reduced residue system modulo b. The size of the complete residue system is just b itself. So if I pick at random an element of the complete residue system, there are b possible choices. How many of them are relatively prime to the base? P minus 1 times q minus 1 of them. So what are the odds of randomly choosing something and having success, having it actually be relatively prime to the base? Well, there were p minus 1 times q minus 1 things that were relatively prime out of p times q total things to choose from. Now, if p and q are primes with a few hundred digits each, then each number p minus 1 over p and q minus 1 over q are very, very, very close to 1. Okay? So if p and q are primes with hundreds of digits, This probability of picking something relatively prime to the base is extraordinarily close to 1. 99.999 and hundreds of nines appear here percent. Okay. Very, very likely that any message you construct will in fact be relatively prime to the base. In practice, therefore, this is really not a very big concern. Okay, it's extraordinarily unlikely that any randomly constructed message will fail to be relatively prime to the base. It's astronomically unlikely. The larger the prime gets, the less of a concern this is. Okay, so the closer and closer p minus 1 over p and q minus 1 over q get to 1, in other words, the larger p and q get, this probability of any message you construct being relatively prime to the base just gets phenomenally close to 1. What about the security of this algorithm? Now, Alice announced her public key, and we openly announced what our message was, n to the k modulo b. So if anyone can determine k inverse modulo phi of pq, they'll be able to decrypt the message. Finding inverses is no problem. Okay, it's just the same successive squaring algorithm. But finding phi of the base is the problem, as I've mentioned already a few times. Okay, to factor this very large b into primes, which is a necessary step to get phi of b, it takes a very, very long time. Okay, factoring large numbers just takes an incredibly long amount of time to do, so it's just not worth it. It might not even be possible if the expected amount of computation is in the trillions of years. For now, okay, as I've said, changes to factoring algorithms or computing techniques might upend this whole system. However, for the time being, factoring large numbers is much slower than multiplying them, so this technique for practical purposes is secure. Okay, now I do want to point out, suppose someone makes a computer that's 1,000,000 times faster than anything else, but it still works in the same methods as conventional computers. This is still not a problem. If I take my primes and instead of having 200 digits, I make them have 400 digits. So I double the length of the primes. This doesn't actually mean that factoring takes twice as long. Every digit you add to the prime is going to double the factoring time, assuming we're talking about digits modulo 2. Everything's being done in binary. So if you add 200 digits to the prime, you're not just saying, oh, it's 200 times slower. It's more like 2 to the 200th times slower. So even if you had 1,000,000 times faster computer, just by adding a few extra digits to the primes that are being used for the security here, you still push this out of the realm of feasibility. And this is why periodically you'll see updates on what bit length of encryption is being used. Oh, 256 bit length? No, not anymore. Now let's use 512. We doubled the amount of bits in our prime numbers effectively. I mean, it means something probably technically slightly different, but for our purposes, the bit length is essentially the size of the numbers in question. So by doubling the size of the number, you really, really slow down factoring algorithms. And in fact, now something like 2048 bit length is, I think, the standard. So we're using very, very large prime numbers, and factoring them is just not practical. So brute force factoring of numbers of this size would take hundreds of trillions of years. So even if all computers were working together, you still wouldn't factor the number within the lifespan of our planet and sun. For now, okay, stuff can change, but this is how we do it for now. So with the algorithm explained, let's work through a simple example. So our friend announces a public key where the base is 1,457 and the exponent is 61. I need to send her the number 903. So what number do I transmit? Well, all I have to do is compute 903 to the 61st power modulo 1457. The successive squaring algorithm knocks this out for us quite quickly. 1,027. So I simply say out loud, 1,027, everybody, isn't that interesting? Okay, another example, if my public key is the base 1457 and the exponent 61, how did I generate my key? Well, it had to be the product of two primes, but let's suppose I actually generated this number, so I know the primes are 31 and 47. So what's my private key going to be? Well, phi of the base is going to be 30 times 46, which is 1380. I chose my exponent to be 61 because it's another prime number and it's relatively prime to 1380. So to compute my private key, I have to compute 61 inverse modulo, not the base, but modulo phi of the base. So I need 61 inverse modulo 1380. This is a common error I've seen students make dozens of times. They attempt to compute this inverse modulo the original base. No, your private key is the exponent inverse modulo phi of the base. But again, computing inverses modulo a known base is fairly quick work for us, and we would end up with 181. So if my friend announces the message 1027 and everyone has heard it, everyone knows that's their encrypted message, how can I recover what they intended to say just to me? Well, I take my private key 181 and I take their message and I raise it to that power modulo the original base of 1457. This is a quick computation and we get 903, which indeed was the original message. So that's how it works. Your public key is a product of two primes and an exponent which is relatively prime to phi of that product. Your private key is then the inverse of the exponent modulo phi of the base. To send a message, you simply take your secret message and you raise it to their exponent modulo their base. When they want to recover it, they take your encrypted message and raise it to their private key modulo that base. So it's pretty quick once you get, once you get it into your mind.